So we're back now to talk about the effects of particle motion in time constant. In other words, these kinds of fields, magnetic fields, where the magnetic fields are allowed to be inhomogeneous in space. Okay, and in particular, we will talk about one kind of interesting drift called the gradient of B drift. Okay, so it's a popular kind. It's also very relevant. Think, for instance, tokamak or a dipole magnetic field. Right? I mean, a dipole magnetic field would look something like this. One half of a dipole at least. Okay, so the magnetic field lines are tighter here, right? The magnetic field lines are spaced closer together here, and they're looser here. So as you move in space, the strength of the magnetic field is varying. D over dx is not equal to 0. There is a gradient in B as you move around. Okay, and this is a configuration that's encountered very, very commonly. And so therefore, charged particles drifting in these kinds of, or rather, the behavior of charged particles in these kinds of configurations is of considerable practical importance. Okay, so as always, you start with the simplest kind of formulation, that of assuming that the perturbations in B, so B is a function of R now, because d over dx or d over dr is not equal to 0, right? It's not constant in space. So at a given R, it comprises a constant term plus a small. This entire thing is delta B. Okay, and the delta B is small. Why is this delta B? You see delta R dot grad. So this would be delta R dot grad B. So you can think of this as a sort of a delta X dot d over dx of, say, B, like that. If you look at it that way, it will be evident, and everything is evaluated at the default position or not. So if you look at it this way, it will be evident why this is the small perturbation. Anyhow, this is written down in a bit of a formal manner, not terribly important to focus on this particular expression, just the basic idea that the perturbations are supposed to be small. They are, and very importantly, small over what kind of length scale? Very, very important. Small, of course, first of all, in physics, always small in comparison with what? Well, delta B is small in comparison to, say, this kind of thing, right? Would be small in comparison with. Okay, so this is one thing. But since we're talking about inhomogeneous fields, small over what kind of length scale? Small over 1 Larmor radius. In other words, if a particle is moving like so, over 1 Larmor radius, let's not perturb the particle's orbit too much over 1 Larmor radius. Okay, say, this would be a Larmor radius, right? So let the magnetic field remain constant over 1 Larmor radius, pretty much. Over about 2-3 Larmor radii, we'll let it change. Okay, so this is very important. If these two are satisfied, then then now intuitively you can sort of appreciate that this will be true, but I would like you to think carefully about why, how this follows from these two. And what is this? This is just that. Just say instead of R, you just take a specialize to a particular coordinate, say Y. Okay, so this would be the gyro frequency, right? This would be the gyro frequency, and the gyro frequency at at a given position Y is approximately equal to a constant value plus, a Taylor expansion. So there is a finite d omega dy. There's a finite, because the magnetic field is changing, the gyro frequency is also changing, but it's changing gently, so gently that just the first term of the Taylor expansion is good enough. Okay, so you can recognize this as just the first term in the Taylor expansion of is enough. Okay, so this is the spirit. Now, you can sort of appreciate that this follows from these two conditions, but I would like you to think carefully and see how this follows from this one and this one. Both of these are necessary. All right. So if this is true, then the concept of the guiding center motion that we talked about earlier is good enough. In other words, if it is true that the gyro frequency varies weakly with length, with its in space, then if you have a situation where where the magnetic field is varying in space like so, then particle trajectory can be like this, and you don't really need, you can average over these fast. This is a fast time scale, the gyro time scale, and you can average over this fast time scale and concentrate only on the guiding center motion. Let me write this in red just to say just these points in red. Say this one, this one, this one, this one, and so on, so forth. Okay, you can afford to follow only these the guiding center. Okay, you can follow just the guiding center. Gee, my handwriting is terrible. Never too good to begin with, and on this particular tablet, it's really bad. Anyhow, so that's that. Now we will talk about this particular manifestation of inhomogeneous magnetic field. Suppose you had a gradient in B, in particular a transverse gradient. Suppose you had a magnetic field out of the page. This is taken from Starok, this figure. So if you had, I'm simply giving you the result on this slide, and we will discuss how this came about. Okay, this is from Starok, but the subsequent discussion on the next slide or so, that's from Boyd and Sanderson. Okay, so you have the magnetic field out of the page. B is along the z direction, and the gradient of B is along the page. Is this? So the magnetic field would be like that, but the gradient is in this direction right here. Okay, and as a result of that, okay, so now the bottom line is, since the gradient is pointing this way, you have weaker magnetic fields at the bottom and stronger magnetic fields at the top. And because of stronger magnetic fields, you have smaller radius of curvature, right? I mean that follows from the equation for the Larmor radius. Do I have that equation mentioned anywhere? The actual equation for the Larmor radius. If not, that's, I mean, you know, I've been sort of assuming that you know it, and that might well be true, but it's good to write it down. I don't have it mentioned anywhere. How about that? It's EB over M. Okay, so how do you get the Larmor radius? Well, you just, you just say M V perpendicular squared over RL is equal to EB. Sorry. Yeah, so MV squared over R is equal to EB V perpendicular. That's it. Okay, so you strike off one of this. So the Larmor radius would simply be M over EB. Right? So this would be the Larmor radius. And so stronger smaller RL, okay, larger RL. You can, okay, so that's obvious from here, right? If B is larger, the RL is smaller. So you can, I mean, in a way, the way I like to always think about this is that it's about who's calling the shots, okay? The V perpendicular is an indicator of the particle's kinetic energy, if you will, or the particle speed. And where did the particle speed come from? I don't know, maybe it's hot, yeah? So it's the thermal speed, right? And the B, of course, is an externally imposed magnetic field. And of course, everything does depend upon the particle mass as well, right? So now if the V, if the particle is very energetic, in other words, it's got a lot of V perpendicular, it says, I don't care about the B as much as a lower energy particle would. So I refuse to be caught in the magnetic field. Okay, I refuse to let the magnetic field control me. On the other hand, if the magnetic field is strong, right, the magnetic field says, I control you, I will force you to spiral around me in a tight spiral with a small Larmor radius. That's how that's one way to think about it. Okay, so anywho, you see here, okay. I hope this rapid scrolling through shows up okay on the movie. So so that's how you have a weaker magnetic field here, larger radius of curvature, and stronger magnetic field here, smaller radius of curvature. And if you really think hard, and this is, so if you really think hard, you can convince yourself of the fact that a larger radius of curvature at the bottom and a smaller radius of curvature at the top will force a positive particle to drift in this direction and a negative particle to drift in this direction. Okay, you can think about it carefully. All right, so that's one thing. That's one way of looking at it. Okay, so a positive particle, for instance, would say I'm drifting like that, but by the time I come here, yeah, so I'm forced to go in a tighter spiral, yeah, but by the time I come down, my spiral increases, and like that, and that's why I have a drift in this direction. Okay, that's the positive particle doing it. So importantly, the direction of the drift is perpendicular both to the gradient as well as the direction of the magnetic field. Okay, now let's derive this a little more, a little more quantitatively. if you will. I don't like to use the word rigorously because it's a little pompous. And, I always strongly believe that physical intuition, going through the maze of equations and fishing out the physics that's way more important or just as important as writing down the equations themselves, right? Just writing down a bunch of equations amounts to very little. You have to be careful with the algebra, no doubt. You have to have a certain facility with the equations to make sure that you don't make mistakes and the assumptions and approximations you're making make sense and so on and so forth. But at the end of the day, it's physics. Okay, anywho. This treatment is from Boyd and Sanderson. Okay, so recall these were the basic equations. X double dot. These were the basic equations for this. Okay, these are the basic equations. And now what you're going to do, of course, is expand. We will be expanding only this. Okay, in a Taylor series, owing to the fact that B can vary, but B varies gently. As we discussed before. Okay. Now, alternatively, it's easier to use complex variables. Instead of x and y separately, you combine x and y in one complex variable like so, and these two equations then can be combined into one equation like this. Okay, and note, the appearance of just this. Please think about why this in itself, writing this down is easy. Not a big deal. There's a double dot here and a single dot here, by the way. But please note this. All right, make sure that you understand where that comes from. Right, and in the zeroth order, this is the equation, right? That gives you gyro motion. Is exactly the same as what you did earlier, with no here. Omega is just taken to be a constant, not this, right? Okay, and now as we discussed before, we are going to perturb omega, right? As a weak function of y in the following manner, and where omega naught. This is just like that. You're going to let omega vary only as a function of y. Okay, what does that mean? Which direction is the magnetic field varying in x or y or z? Please think about it. Okay. For the purposes of this one, we're simply saying that the gyro frequency varies as a function of y. In other words, for instance, here you see the gyro frequency will vary in this direction. Okay. Okay. Right. Now, the spirit of the approximation. Okay. So using this, you plug this in. You plug this in here. Yeah. The spirit of the approximation is that y and omega naught on the right hand side can be replaced by their uniform B field values. This is the the basic trick, if you will. Okay, and this is the not so much trick as this is the essence of the approximation, the slowly varying approximation. Okay, then you can you can verify that this allows for this equation. Allows for this kind of solution. Okay, so this is a sinusoid, right? So you if you're uncomfortable with it, plug it in to see if it works. Okay, yeah, with the for first time derivative of psi is equal to this. Okay, where we're yet to define alpha, I hope. Okay, alpha is simply a phase factor. Okay, not so important. It's just a phase. Okay, so so this is the substitution. This is a substitution. I assume this kind of a solution with with this being given by this. I substitute and I get this. Okay, integrating once. So this is and I at the end of the day I want psi as a function of t, and then from psi I'm going to get x as a function of t and y as a function of t. Right. So integrating once, so this is what, I mean, I'm skipping steps here, but integrating once gives you x as a function of dx dt. Dx dt looks like this. So you've got something like a cosine 2 omega, you've got a constant term, yeah? Well, you've got a cosine oscillation, right? Minus, you've got a constant term and a cosine 2 omega, right? A 2 omega is a fast oscillation. Okay, and also a sine. So this and this are kind of on the same footing. Okay, but this is a faster oscillation. All right, and with a similar expression, with exactly with an expression for y dot t, it looks very similar, except you'll have a sine here, a cosine here, and a sine here, a sine here, and a cosine here. But importantly, this will be missing. There's no constant term. Okay, all right. So fine. What about it? So just to recall the expression there. Now, really, what in the spirit of the slowly varying drift, and in the spirit of this. In the spirit of this kind of slowly varying gradient of B, and really in the spirit of the expansion of this, we can average over the gyrofrequency term. In other words, the gyrofrequency drift is a fast time scale. You can average over it, and if you're averaging over the gyrofrequency drift, you can definitely average over the twice gyrofrequency drift also. Therefore, the average of V, the average of x dot, okay, once you average it, this would be the x component, this would be the y component, and this would be the z component, and we simply call it V parallel in as much as it's along the direction of B. So this corresponds to the famous grad B drift, and this is the same thing written in vector notation. Okay, I'll explain what this is. So the main thing is that you see the main thing here is that you see, even here it's evident the B is along this direction, okay, and the gradient was along the y direction, and the direction of the drift is along the x direction, which is perpendicular to both the gradient as well as the B, and that's very clear from this kind of expression. Yeah, the drift is perpendicular to both B and grad B. I believe this is simply 1/2 B perpendicular square. That's what this W. Please verify this. I don't want to vouch for this at the moment.